So having seen kinetic energy, having seen potential energy, now we are in a position to understand mechanical energy. So as you know, mechanical energy comprises of these two things, kinetic and potential. So first of all, you should be clear with the system. You define the system clearly. Once you define the system, then note down the kinetic energy, complete kinetic energy. If the system is made up of three bodies, you should add the kinetic energies of each of the three bodies to get the total kinetic energy of the system. And then you have potential energy also. You have to calculate the potential energy also of all the due to mutual interaction. Then finally you add them to get the total mechanical energy. So total mechanical energy is equal to, I will denote it by E. It is equal to the sum of kinetic and potential energy. Remember, energy is a scalar quantity. So ordinary addition. You have to follow ordinary addition to get the total energy. Energy is not a vector. So it's very simple. Scalar quantities are easy to handle as compared to vectors because vectors have direction. Okay. So now listen carefully what I am telling because I am about to state law of conservation of mechanical energy. If you are clear with the definition, then only you will be able to apply it perfectly. So the definition should be clear in your mind. Then application becomes easy. So as I told you, first to identify the system, then in the absence of external work done, means external work done should be zero in a process, in any phenomena involving conservative fields. Because potential energy carries meaning only in conservative field. So if external work done is zero, then total mechanical energy of the system will remain conserved. Total mechanical energy of the system will remain conserved. Okay. So it is like this. We can understand this, very simple. You assume kinetic energy as gold. You can assume kinetic energy as gold. Potential energy is your bank balance. Gold and land, suppose gold plus land is your kinetic energy. Real estate, land, house, building, all this comes under real estate plus gold. So now, in the absence of external work done, means outside person did not pay you even a single rupee. Any third person did not put any amount in your account, bank account. But your bank account plus your real estate, that is land and gold, etc., total will always be same because you didn't spend it in any other thing. Neither any other person gave you any money. So your total. So maybe what you are doing, you are taking some amount from the bank and you are purchasing gold. So total work remains same. No. Suppose you purchased gold worth 2 lakh rupees. Even though in the bank balance 2 lakh will reduce, but you have gold worth 2 lakh. So total is still the same. As long as any third person did not put any money in your bank, neither did you spend the money in any other form. So in the absence of external work done, external work done should be zero. Then total mechanical energy remains conserved or constant. So external work done is zero can be in two different situations. Okay. So we will discuss when external work done is zero. First case, there are no external forces. It's possible. There are no external forces. So if there is no force, there is no question of any work done. So in the absence of external forces, the work done by external force will be zero. The other possibility is that external force is there, but the force is at right angles to the displacement. So work done will be zero. Okay. For example, a simple example. Suppose a smooth body, smooth body comes down an inclined plane. Okay. A smooth block comes down an inclined plane. In the free body diagram, you will find that you have only two forces, namely the weight and normal reaction. Weight is a conservative force. So we are talking of external force. System forces are not taken as external. So what is external force here? Normal reaction. Even though normal reaction is there, but movement and normal reaction are at right angles. So work done by normal reaction is zero. Similarly, another example, suppose you have a simple pendulum like thing and you give a tangential speed so that it goes up. So when in the free body diagram, you will have weight and tension, that's all. These are the two forces in the free body diagram. But work done by tension is zero. Why? Because displacement is tangential and tension is radial. Angle between tangent and radius is 90 degrees. So in certain cases external forces will be there, but still work done will be zero. And in certain cases there will be no external force at all. So under these situations, you are free to apply change this law of conservation of mechanical energy. So if we differentiate this, both sides, that we have delta E is equal to delta K plus delta U. But since energy is constant, its change will be zero. When you differentiate, derivative of a constant is zero. So that means it is clear that delta K is equal to minus delta U, or delta U is equal to minus delta K. That means there can be a loss in potential energy and equal gain in kinetic energy, or vice versa. Isn't it? For example, in a projectile motion, as you throw the body up, what happens as it during its ascent, its potential energy is increasing. So kinetic energy will decrease by an equal amount. Similarly, while it is descending, its kinetic energy will increase because speed is increasing, but potential energy will decrease by an equal amount. Because there is no external force. When you throw a projectile, the only force acting is its weight, and weight is a conservative force. We are talking of external force, not the conservative forces. So there is no external force, so no work done. So you can apply law of conservation of mechanical energy on a projectile. Of course, we are ignoring the air resistance. Is that clear? Increase in potential energy will be equal to decrease in kinetic energy and vice versa. It's clearly indicated. Application, you'll be able to apply. Just you have to ensure that external work is zero and it has to be a conservative field.